the New Earth Fourth Hydrogen Energy Development Conference afternoon sessions. So we are commencing to have our next talk delivered by our speaker, Professor Leung, Kwok, Michael. Engineer Professor Leung is the chair professor of renewable energies and the director of the Abilities R&D Energy Research Center in the School of Energy and Environments at the City University of Hong Kong. He also a researcher and also academics in this specialized in these areas. Today he is going to deliver topics of hydrogen fuel cell developments. So, ladies and gentlemen, please welcome our next speaker, Professor Leung.
Okay, thank you for your kind introduction. And I'd like to also thank Engineer Stephen Chen and Dr. Leung for organizing this event, okay, so that we have an opportunity to share our expertise in fuel cell and hydrogen. Okay, so I would like to share with you our recent research in green hydrogen production and how we use fuel cell to convert the green hydrogen into electricity. And I would like to show you some of our recent research so that you will find that there is a lot of development to enhance the technology. Okay, so my presentation will cover the following challenges: green hydrogen production, green ammonia production. Ammonia is a way to store hydrogen in this approach. And then I will talk about fuel cell and also our research on the novel photocatalytic fuel cell. Okay, I think the background information is, I don't need to spend much time. Okay, we all know that we have energy crisis, environmental problems, and renewable energy is our ultimate solution. Okay, we can harness solar energy, wind power, okay? And however, the renewable energies are intermittent. Therefore, we need to have storage. So today we rely on batteries. Okay? And hydrogen is an alternative. Okay? So here I have some information about the trend for the cost of different energy storage methods. Okay? So I'm showing that we have battery, fuel cell, and this chart also include fuel for internal combustions as a reference. So based on these data, okay, this reports the life cycle cost, okay, for different approach for vehicles. Okay, so it shows that today's battery is maybe relatively cheaper than fuel cell. Okay? However, in the future, okay, the technology will be developed better, and fuel cell will be at a lower cost. So this is why we have to start to use hydrogen and fuel cell today. This is another chart to show, okay, what are the possible form of storage of hydrogen. So here it shows that if we consider the amount of energy stored and how far we have to be transported. Okay, Then on the left-hand side, if we have small amount of hydrogen productions and we want to transport hydrogen to distribute in the local city, we can choose pipeline. Okay? We have TANGAS. Okay? TANGAS have pipeline in Hong Kong for hydrogen transport. Okay, if we produce hydrogen and then we want to transport it to a farther distance to maybe in other countries by shipping, hydrogen is very light. Okay, so an effective way is to liquefy or at high pressure. Okay, then liquid hydrogen, okay, is an option. And then on the right-hand side, okay, if we have to transport this fuel to a farther distance, okay, ammonia may be a better option, okay, because liquefied ammonia consume a lot less energy compared with hydrogen. I will have later on some more information for this reference. Okay, so to move on, okay, to run the fuel cell, okay, we need to have green hydrogen. Okay, if we want to reduce the carbon emission to zero, okay, we have to begin with green hydrogen production. Here I introduce a number of promising hydrogen production methods. The first one is by means of electrochemical methods. That means if we have surplus electricity generated from our solar PV plant or our wind farm, okay, then the electricity can be used to drive an electrolyzer to decompose water so that we have hydrogen as a product. Conventional electrolyzer, well, the most important component in this system is the catalyst as the electrode. Platinum is what we commonly use in today's industry. However, if we want to reduce cost, okay, we have to develop more effective catalyst. At the same time, it is at lower cost. This also further presents, okay, to what we need, okay, in order to achieve water dissociation. Okay. We need to induce some water reduction reactions, and also we have to including hydrogen evolution reactions and oxygen reduction reactions. Okay, so here I show some of our recent work, okay, how we developed better catalysts, okay. So I may not go into the much details, okay, but here shows some of the innovations in this research. Okay, so first of all, the material, instead of platinum, okay, we can choose other metal compound. In this study, we use molybdenum disulfides, okay, which can effectively decompose water into hydrogen and oxygen. On top of this, we developed the catalyst in a nanoscale so that it can improve the reactive surface area. Moreover, the surface will be developed in a multi-axis form. So in catalysis, we understand that if the materials axes are most reactive, okay, because it exposes a lot more to the environment. Okay, this is another materials we developed. Okay, this is also an electrochemical catalyst for hydrogen productions. In this materials, this is a composite materials. It includes, again, molybdenum disulfides, and this integrated with cobalt, carbon nanotube. The two materials have different functions, okay, but we have to put the two functions together to increase the hydrogen production effectiveness. If in this materials, palladium disulfide can dissociate water, and then the copper will facilitate the combination of the protons, 2 protons, to form hydrogen. Okay, so this is some of the work we do every day in our laboratory to study the materials. Okay, okay, number 2 is green ammonia. Okay, so why do we, we know hydrogen is what we need, okay, but ammonia is an alternative, okay? And why we need to produce ammonia, okay? So here, it shows one of the strategies to implement the hydrogen fuel, okay? We can build our central green hydrogen production plant at a place where the renewable energy resources are rich. For example, in the northern part of the country, in Mongolia, okay, the sunlight is strong and the wind speed is high. So we can build our renewable energy plant and produce large amounts of hydrogen or green fuel, okay, in this central plant, and then we can ship the green fuels to different parts of the world. So for this strategy, all the green fuels have to be transported long distance. Hydrogen is what we want, but if we want to transport hydrogen to a very far distance, hydrogen has to be compressed to high pressure, as much as 700 bars, or liquefied in order to store it effectively. To store liquid hydrogen, we have to cool it below the boiling point, that is minus 200 degrees Celsius. Alternatively, ammonia is a compound that contains a lot of hydrogen atoms. So it is a form of hydrogen storage. And to liquefy ammonia, the temperature is a lot higher, minus 33 degrees Celsius. So that means that the storage of ammonia is a lot more energy efficient. Okay, so in our research, we developed the catalyst, okay, for ammonia productions. Okay? So this is another material. It looks very complex. Okay? The concept is it mimic some biological process. Okay? In the biological world, ammonia is produced in different ways. Okay, so this is a chemical that models the biological process. So it also includes what I mentioned, palladium. It also includes cobalt. And different materials also perform different functions. When all these functions are integrated together, ammonia will be produced. Okay, for example, the palladium can split nitrogen. We have nitrogen in the air. Okay, we have to, number one, to split the N2 into single atom nitrogen, and then the nitrogen has to immediately react with 3 protons to form ammonia. So this material is purposely designed to perform these functions. Okay, this is another material, another catalyst for ammonia productions. Okay, this is cobalt, palladium, bimetallic atomic pairs. That means the 2 chemicals are fabricated, and they are fabricated in the form of single atoms. And in catalysis, we also understand that. Okay, the smaller the particles, the more reactive the chemical reactions will be. So the smallest particles will be a single atom. Okay? So we produce these materials, and we also test their ammonia production performance. Also find that the reaction are very active. Okay, so these are some of the electrochemical methods. Another method is also more novel, more innovative. This is photocatalytic hydrogen productions. That means the catalysis will be activated by light. So we will use sunlight because sunlight is free of charge. Okay. So some concept of the solar photocatalysis, okay, when the chemicals is activated, it produces very strong oxidizing agent, such as hydroxyl radical, and also very strong reducing agent, that is a free electron. Okay. So let me sidetrack a little. Okay, or recently we successfully applied this photocatalysis to produce a new product. This is a photocatalytic anti-fouling paint to prevent the growth of unwanted marine organism growing on the bottom of the boat or growing in the marine facilities. Okay? So we also developed our own products, okay, in this research. Okay, back to today's topic. We also apply the same technology, solar photocatalysis, for green hydrogen productions. So that means when the photocatalyst is activated, the electron produced can decompose water to form hydrogen. Okay? So this is one of our earlier laboratory tests, okay, for the proof of concept. And then more recently, we further design our nano photocatalyst, okay, for improved performance. Okay, so this is one of the materials we developed, this is another material developed based on another metal oxide, bismuth validate, combined with sulfur bromide. Okay? So all these materials are purposely designed so that they can make use of their solar spectrums and activate their chemical reactions for hydrogen production. Photocatalytic process can be also produce ammonia. Okay? So here it shows the materials we produce and also the performance we measure for ammonia productions from these materials. Okay, so let's move on. Okay, so now we have new technologies to produce green fuels. Then the next step is how we use the fuel to produce electricity. So we have fuel cell. Okay, fuel cell. Okay, you probably have already heard about this in the morning sections. Okay, so the fuel can be converted by electrochemical process to produce electricity. The background, it was for space applications, and today we have commercial products for larger scale, okay, for buildings applications, and of course we have fuel cell cars, we also have fuel cell bus. Okay. And the driver is me. Okay, the best car I've ever driven. Okay, so the fuel cell cost is already driven down to a competitive level. Okay, a fuel cell car can compete with internal combustion engines. And in order to further reduce costs, okay, we have a better fuel cell. Okay, I mentioned photocatalyst before. Okay, so photocatalyst can combine with fuel cell. Okay, so that the advantage is that this system can perform some environmental functions, such as wastewater treatment. Okay, it can decompose the organic waste in wastewater, and the process will also generate free electrons flowing in one direction. That means free electricity. Okay? So this is the purpose of this system. Okay? So we have a lot of research to further enhance the design of photocatalytic fuel cell. Okay, so time is limited, so I have to conclude my presentation. So this could be a poster that summarized all the technologies I have just mentioned. Okay, we have to develop a green fuel, okay, in the form of hydrogen or ammonia by renewable energies. And then we also should have a very effective fuel cell, okay, to convert the fuel that store energy, convert the stored energy back into electricity for our energy demand. Okay, okay, so at the end, I would like to acknowledge my research team and the financial support from different forms of funding. Thank you.